Welcome and thank you for joining. In this lesson, we'll explore exponential equations. Now, first of all, an exponential equation is an equation that contains, guess what, exponential terms. And the variable we need to solve for is either in the exponent or in the base of the exponential term. Now, to solve an exponential equation means to isolate the unknown variable, and when we isolate the unknown variable, we need to simplify the terms in the equation. Now, since the terms are in exponential form, we need to use the exponent laws to simplify. So let's review the exponent laws one more time. So there are three exponent laws. Number one is the product law that states that two exponential numbers must have the same base in order to multiply. And when you multiply two exponential numbers, the base remains the same, then we add the exponents. The next exponent law is the quotient law. So this is when we divide two exponential numbers. Again, similar to multiplication, we need the bases to be the same. Otherwise, we cannot divide by using this particular rule, and we're going to keep the same base in the answer and simply subtract the exponents. And the last law is what we call the power law. This is when we bring an exponential number to another power. And in this case, we keep obviously the same base. We only have one base here, and we multiply the powers. Now, there are only three exponent laws, but there are many exponent properties, we call them, and that we use in simplifying exponential expressions. And all properties are derived from the three exponent laws. So I'm going to make a list as comprehensive as possible here. So rule number one, a to the power of 1 is equal to a. Rule number two, any number to the power 0 equals 1 besides number 0. So 0 to the power 0 is actually undefined. Try to use a calculator to see it. And I've also made a small little video where I explain exactly why that happens. Next rule that I want to mention is number 1 raised to any power would be equal to 1. And the next one, we have a to the power of a negative exponent is equal to 1 over a to the power of the positive exponent. This is how we convert negative exponents to positive, by flipping the base. So you can look at it as the base with denominator 1. So you flip the base to 1 over a, right, to the power of m. So 1 to the power of m is equal to 1, and then a to the power of m down here. Next rule is similar to the previous one. If the negative power is in the denominator, we can make it positive by bringing the number up in the numerator. A few more to go. So if we have a fraction to the power of a negative, then we can change the sign of the exponent from negative to positive by flipping the base, so from a over b to b over a. And lastly, we have the distributive property. That's what this is called. If we have a base that is made by the product of two or more terms, then and all of them raised to the power of n, this power will be distributed to each and every part of the term, so to each and every factor in the base. So now let's take a look at solving exponential equations. So we said that in exponential equations, we'll see that sometimes the unknown will be in the exponent and sometimes in the base. And I will emphasize that in every example, so which one is what. And we're going to start with our first example. Now, on the side here, I also wrote the steps. So if you want, you can pause the video and try to follow the steps on your own. It's a different experience when you try to explore or try to follow the instructions when you're trying to learn something new. And I think that this is a little bit more rewarding in a way. But here we go again. 5 to the power of 2x minus 4 equals 5 to the power of 12 minus 2x. So this is an example where the bases of the exponential terms are the same, so base 5, and we have a single term in each side, and both bases are equal. So the fact that these two are equal assumes that the exponents must be equal as well. So in this case, we are going to say that 2x minus 4 is equal to 12 minus 2x. So 2x minus 4 equals 12 minus 2x. So again, we're going to use this strategy when the bases are already the same. So we simply equate the exponents. So two things we need to remember: not only bases are the same, but we have a single term on each side of the equation. And now we simply solve this very simple linear equation for variable x. So keep the numbers to the right, or bring all the numbers to the right, variables to the left, and then we get 4x equals 16, from where we get x equal to 4. Now, if you want to check your solution, to check and see if this works or not, so we substitute x by 4. So the left side, 5 to the power of 2 times 4 minus 4 equals the right side, which is 5 to the power of 12 minus 2 times 4. So as you can see on the left side, we have 2 times 4, 8 minus 4 is 4. And the right side is 12 minus 8, and that is equal to 4, so 5 to the power 4, which tells us that the left and the right side are the same, so the solution works. Now, let's take a look at another example. So the examples will get slightly harder, not that hard, really, not that complicated, just so that we can acquire new skills. So in the next equation, example 2, we have 8 to the power of x equals 4 to the power of 2x plus 1. So what I see here is a single term in each side of the equation, which is similar to the example number 1, but the problem that I'm encountering here is that the bases are different. So when this happens, we try to write the bases with the same base, or as exponential numbers with the same base. And when you look at numbers 8 and 4, you see that they're both multiples of 2. So we're going to try to write number 8 as an exponential with base of 2. So the way you do it is just use a calculator. So this is obviously a simple term, a simple small number, but normally what you want to do is pick a base that you think should fit into the basis given, and then try different powers by trial and error on the calculator. So this is going to be 2 to the power of 3 for 8, and then to the power of x. And then number 4 is 2 to the power of 2, and then to the power of 2x plus 1. So we want to simplify each side. As you can see, we have arrived to the same base in both sides of the equation. And we'll have on the left side 2 to the power of, here is the power law, so you multiply the exponents. And on the other side, we're going to have the base 2, and then the exponent will be 2 to the power of 2 times 2x plus 1. Now, as you can see, now we have the exact same basis. The only difference is the exponents, which we need to equate in order to make these two exponential terms equal. So 2x plus 1. And as you can see here, we have a simple linear equation. 3x equals 4x plus 2, so 3x minus 4x is equal to 2, so negative x is 2, which will make the value of x equal to negative 2. So if you look at the steps that are described in here, we have to express first the terms on each side as exponential terms with the same base. And I added another example in here, just in case, and then equate the exponents and solve for the unknown variable. Okay, so we're going to move on to another example similar to this, but we're adding something in addition to what we had in the previous example. So we still have a single term on each side of the equation. So what does that mean? So, well, we have a bunch of terms multiplying each other, which means that this is one term and this is one term. Now, the way that we solve exponential equations when we have one term on each side is by trying to first make their bases the same, so that then we can equate their exponents. So as you can see in here, you have number 4 multiplying 32 times to the power 4x minus 9. Now, a common mistake that I've seen people make easily is multiplying 4 by 32. Now, we don't want to multiply these two numbers first because 32 is the base of an exponential number. So bad math won't allow us to multiply because the exponents, which are here, have priority over multiplication. So multiplications turn doesn't come before the exponents. So what we're going to do in this case is try to reduce coefficients. Now, what that means is that when you look at the left side, you have a coefficient of 4, and on the right side, a coefficient of 16. The exponential part of the equation will be 32 to the power of 4x minus 9, and then here is 16 to the power of 3x plus 5. So we'll reduce the coefficient, so we'll divide both sides by 4. And that will make the equation look like this. We have a 32, obviously 4 over 4, 1 to the power of 4x minus 9 is equal to 4, and then 16 to the power of 3x plus 5. So here we have a single exponential term, no coefficients anymore, but here we have a coefficient and an exponential term multiplied together, which make a single big term. So we're going to continue with the same strategy in mind. So we're going to try to make the bases the same. When you look at each base in both sides of the equation, you see that we have a base of 32 and a base of 16. So a base of 32 can be written as 2 to the power of 5. It's an even number. That's the first that would come to my mind. And that would change the left side to become 2 to the power 5 to the power 4x minus 9. Now, the base of 16 is 2 to the power of 4, and still to the power of 3x plus 5. So basically what we did in here was write number 32 as 2 to the 5 and 16 as 2 to the 4. Now, you're probably wondering what we're going to do with this term. Well, as you can see in here, we can't simplify more because if we divide both sides by 4, then we will have to get coefficients here, so that won't help. So what we are going to do, though, is we're going to try to write number 4 also as an exponential with base 2. So 4 is 2 squared. So next, we'll try to simplify each side, and our ultimate goal is to write both sides or each side as an exponential with a single base. So we have 2 to the power of 5 times 4x minus 9 is equal to, now here we have a couple of laws that we want to apply. So we have 2 to the power of 2 multiplied by 2 to the power of 4 times 3x plus 5. So the left side will remain the same. If you want to, you can start expanding in here. That's totally fine. And I would write 20x minus 45. And on the right side, we're going to have to write this term here as 2 to the power of 12x plus 20. And obviously, we still have the 2 square here. Now, it's time to combine these two terms together. So they're exponentials of same base. So left side is, 2 to the power of 20x. Almost forgot that. 20x minus 45 is equal to 2 to the power of 2. Because of product rule, we are adding the exponents, and that will become 12x plus 20. And now we have exact same basis on both sides. Now, I'm taking a lot of steps in here, and I know that you're very skilled at working with exponent laws, and you can simplify these expressions in probably half or less than half of the steps that I used. But I'm just trying to explain everything so everyone knows and sees where the terms are going and no one is getting lost in the process. So as you can see now, we have the exact same base in both sides of the equation, which tells us that since the two exponential terms are equal, their exponents must also be equal. So we're going to say 20x minus 45 is equal to 12x plus 22. So combine the x's. It's a linear equation, right? So in linear equations, we always take the variables in one side, numbers in the other. And we obtain 8x on one side here, and the other side is a 67. So the value of x in this case is 67 divided by 8, and that would be the solution to this equation. Now, we're going to take a look at the next group of equations, which are quadratic exponential equations. And for this, please follow with the video. Bye for now, and thank you for learning with me.